All right, 3.2 video notes, parallel lines and transversals. If you notice, we're skipping 3.1. There's only a few definitions and vocabulary in 3.1, and we've kind of merged 3.1 and 3.2 together. So before we get started on this set of notes, I would like to just do a couple definitions here and a couple diagrams before we get started. So first of all, let's define parallel lines. So parallel lines are two lines in the same plane, that part's pretty important, that never intersect. They never cross each other. And you've probably learned about these, for quite a long time now. But basically, so you have a line, and we'll call this line L, and then you have another line that we'll refer to as M. And if line L and line M are never going to cross, then we say that they are parallel. Now the symbol for parallel is just two straight lines vertically up and down. That's the symbol that represents the word parallel. So in the future, I probably won't write the word out. I'll actually draw that symbol. Now some people might say, well, how come I can't just say two lines that never intersect? Because what's the whole purpose of this same plane part? So I want to draw another diagram, a three-dimensional box or a rectangular prism here. So I'm going to draw a box, and I'd like you to draw this with me. So here's a box, and on this box I can draw two different lines that also will never cross. If I draw a line through the front edge of this box down here, but then up top I draw another line through this edge of the box, these two lines are also never going to cross. So it's not good enough to just say two lines that never intersect. These two red lines never intersect, but they're in different planes, and we call those skew lines. So I'm going to define those right now as well. Two lines that do not intersect, that lie in different planes. So there is a little bit of a difference between just lines that don't intersect, whether they're parallel or whether they're called skew lines. One other word I'd like to mention here is anytime you have another line intersect two different lines like that, such as this blue line, we'll call this line N. This line has a name. Whenever you cross two lines like that, you are referred to as a transversal. So transversal is another vocabulary word that we're going to see here in the 3.2 notes. These are basically the key ideas from 3.1 that'll set us up here for 3.2. All right, let's jump back into the notes. All right, so postulate 3.2.1, the corresponding angles postulate. Corresponding angles are a special pair of angles. And it says if two parallel, so notice the conditional statement here. This is our P. If two parallel lines are cut by a transversal. So if that happens, then the pairs of corresponding angles are congruent. So corresponding angles are basically angles that are in the same position. Okay, angles that are in the same position. So if you look at the diagram here, angle 1 and angle 3 are both in the same position. So angle 1 is congruent to angle 3. Also, angle 6 and angle 8 would be in the same position. So they are congruent and they are called corresponding angles. Angle 2 and angle 4 match up with each other. They're in the same position. So they are corresponding angles and they are congruent, the same measure. And then finally, angle 5 out here and angle 7, those two are in the same exact position. So whenever you have angles in the same position with parallel lines, they are definitely going to be congruent. So let's go ahead and go down here and work out a couple examples. So in each example, find x, and then can you find the measure of all the angles? So looking at this first one here, I can find all the angles in this first intersection here where the 80 is based on stuff from chapter 1. If you remember, the angle right below it right here is a vertical angle, so they are equal. The angles adjacent to it form a straight line, so they add up to 180. So we have some linear pairs and vertical angles. So that intersection, I kind of refer to this as an intersection. This intersection is easy to figure out with chapter 1 material. But now we can use the postulate up above that says, hey, wait a minute, every one of these angles, if you look down to the next intersection, the people in the same position should be congruent. So this 80 matches up with 80. This 100 corresponds with this 100. This 80 goes with this 80. And this 100 goes with that 100. So I use corresponding angles to move from one intersection down to the other intersection. That's what the corresponding angles postulate will do for me. Now we can also do this using algebra problems. If I look at the next diagram, I'm giving an expression for this angle and for this angle. And so because of the postulate up above, I know those two angles have to be congruent. So I can set up an algebra equation, and then I can start solving it. I can subtract an x from both sides, which gives me x minus 45 equals 30. I then can add 45 to both sides, which tells me that x is 75. Then I can actually go back and I can substitute 75 in to find out the true angle measures. For instance, in this first expression, 2 times 75 is 150, subtract 45, that's 105 degrees. So immediately I know that this is 105 degrees. Because of vertical angles, I can fill in the kitty corner angle here. And now I can use linear pairs to figure out the rest of them. These two angles here have to add up to 180. So that's 75, 75, 75, and 75. And you'll always see this pattern. If you notice in both pictures, there are only two different angle measures when it comes to parallel lines. You're either equal or you add up to 180. All right, moving on down, we have three theorems here that we're going to kind of have to memorize. And I'm going to move this over to the edge to give myself a little bit of room to draw a diagram. So some of the key words in these theorems here actually refer to the interior or exterior of parallel lines. So when you draw two parallel lines, this region inside here, this whole region in the middle, this is called the interior region. And then outside the parallel lines on both sides is called the exterior region. Now, a lot of these also, when you name these angles, they depend on where the transversal is. So if the transversal comes running down, you're either on the same side of the transversal, meaning that you're on the right side of the red line over here, or you're on the left side of the red line. So if you're on the same side, you're called same side interior, and you'll notice that terminology over here. If you're on different sides of the transversal, you're referred to as alternate. So the first word, same side or alternate, refer to this transversal here. And the second word, the interior or the exterior, talks about whether you're inside or outside the parallel line. So that kind of determines your position and what pair you are. So if we look at these theorems, and again, they're all written in if-then form, but the first one is the alternate interior angle theorem. It says if two parallel lines are cut by a transversal, which that's this diagram over here to the right, then the pairs of alternate interior angles are congruent. So alternate interior means we're on the insides of the parallel lines, but we're on the opposite sides of the transversal. So angle 1 and angle 3, just like over here in the drawing, angle 1 and angle 3 are on the interior. They're inside the parallel lines, but they're on opposite sides of the transversal. And similarly, 2 and 4 would also be alternate interior angles. And the theorem says that they are congruent. So we will know that this angle and this angle have to be equal to each other. And these two angles are going to have to be equal to each other. And we kind of saw that in our earlier examples, but now we just formally have a definition for it. Alternate exterior, this is opposite the transversal, but on the outside, they are also congruent. So we're talking about angles here like angle 5 and angle 7. They're on opposite sides of the red line, opposite sides of the transversal, but they're on the exterior, they're on the outsides. And they are also going to be congruent. So this angle is going to match this angle. And similarly, we can do 6 and 8. Angle 6 and angle 8 are the second pair of alternate exterior angles, and they're also going to be congruent. Now, the pair that's different from all of these, and I'm gonna kind of draw another diagram right below it. The pair that's different between these is same side interior, same side insides. So same side insides would be like angle 1 and let's say angle 2 in this drawing. Okay. Now I can just see that angle 2 is an acute angle. It's less than 90 degrees. Angle 1 is obtuse. It's larger than 90 degrees. So same side interior angles are not they're not congruent. They are actually supplementary, or they equal 180 when you add them up. So that's the one that's different. So basically you have 4 pairs that you need to know about: alternate interior, alternate exterior, same side interior, and then the first one up top, the corresponding angles. And you're going to see some of those in your practice today. Alright, let's scroll down and look at some examples. So find each angle measure. Some of these involve algebra, some just involve numbers. So looking at my picture here, and one thing I also didn't mention, these little red arrows, they represent parallel lines. So if I wanted to, I could say that line BC is parallel to line DE. That's one way I could let you know you have parallel lines, but the other way is to simply put a set of arrows on them, and that also lets you know that the lines are parallel. So let's go ahead and let's fill in these angle measures. We need to find the measure of angle EDF. So EDF is down here where the X is, and these two angles are equal. Okay, X is 125, and what pair are they? They're on the outside of the parallel lines, so they're exterior, and they are on opposite sides of the transversal. One's on the right and one's on the left here. So these are what's referred to as alternate exterior. That's the pair. And I could find all the other angle measures if I wanted to. This is also 125, 125, and I can play the 180 game. So this would be 55 and 55. And it's like a copy paste. Whatever happens in the top intersection happens in the bottom intersection. Alright, over here on the next side, when I'm looking at these, I first identify, here are my parallel lines, and here is the transversal. So I look at the angles that are given to me, and the two angles in question are here and here. Well, when I think about what pair they are, they're definitely both on the interior. Okay, so they're interior, and they are the same side of the transversal. And I know that same side and interior are supplementary. They have to equal 180. So I'm going to set my equation up. 13x plus 23x has to equal 180. And then I can work this thing out. Combine like terms. Divide both sides by 39. And that goes in there, what? 180 divided by 39. Grab a calculator here. I believe it's going to be 5. X equals 5. And when you plug it back in, it should work. When I plug it in, 13 times 5 is 65. 23 times 5 is 115. So yes, they do add up to 180. Things are looking pretty good. Alright, this next diagram, don't really love the setup. I see the parallel lines. I see the transversal. The problem with this diagram is it's kind of arbitrary what angles these two represent. I'm pretty sure that they meant the 3x minus 15 goes here, and the 2x plus 10 goes up there. Because otherwise, if they were side by side, it would just be a linear pair, and we wouldn't really be dealing with the chapter 3 vocabulary. So these two angles, since they're both on the interior, They're on the inside of the parallel lines, but they're alternate. They're on opposite sides of the transversal. Well, alternate interior angles have to be congruent according to the theorem up above. So I'm going to set these two equal to each other. 2x plus 10 equals 3x minus 15. I'm going to subtract 2x from both sides. And then I'm going to add 15 to both sides. And I get x equals 25. So now finding the true measure, they wanted me to find the true measure of ABD. I plug 25 in there. 2 times 25 is 50 plus 10. ABD would be equal to 60 degrees. Diagram on the right. I'm not going to do this example. We've already done one, like several of these like this, so I'm not going to worry about that one. Let's move on down to a couple here on the bottom. These get a little bit more challenging. These are both standardized test questions that have been pulled from either SAT or ACT. So find, it says the measure of angle RST, which is right here, that's x plus 50, and STU is 3x plus 20. And we need to find the measure of angle RVT. So what we're really after is we want to figure out how many degrees is that angle right there. Alright, well this one's kind of tricky because I'm going to extend these parallel lines a little bit. These are called auxiliary lines. I'm going to draw an auxiliary line through these parallel lines so it becomes a little bit easier to see what's going on. And if you notice, I have two sets of parallel lines. That's what the arrows on those lines represent. I think when you extend it out like that, it makes the problem a little bit easier. So let's go ahead and try to tackle it. Well, when I look at these two angles that were given to me, I notice that they are on the interior of the blue lines, of the parallel lines, and they're on alternate sides of the transversal. So these two are alternate interior, which I know have to be equal. So I set up my equation, x plus 50 equals 3x plus 20. And I'm going to solve this. I'm going to subtract x from both sides. And then I'm going to subtract 20 from both sides. And I use the division property to divide by 2. And I will get x equals 15. So when I plug x equals 15 in there, 15 plus 50, that would make this angle up here 65. And that would make this angle 65 because they're vertical angles. Play the linear pair. I have 115 and 115. If I plug 15 into this bottom one, I also get 65, 65, and 115 and 115. Now, if I change my focus, and I focus now on the red lines being the parallel lines, and this green line being a transversal, okay, being a transversal, I'll notice that these angles should correspond with all of these angles. They should match up. It's a little tougher when you have 4 lines instead of 3. So now I can see that 65 corresponds or is in the same position with the angle that they asked for. So the correct answer would be C. Alright, last example. I'm going to leave this one up for you guys to try in class. I'd like to actually try this one together and see what you guys come up with in class. So this is kind of a challenge problem. This was taken off of an ACT test, and it was one of the tougher problems that year towards the end of the test. So I'd like to kind of see how you guys battle with it. All right, those are your notes. Be ready to get after some practice today. See ya.